Hello? I can't hear anything. Okay.
Thing. Hello?
I can hear you now. Okay, I thought it was me because I was
And
on
am
my
I,
iPad and then I'm on my phone.
am I an appropriate volume? Because it looks like my volume is really low.
No, I can hear you perfectly on my phone.
All right. So apparently the USB port I was in just doesn't work. Good to
Oh,
know.
okay.
I was just assuming everything was fine.
Mhm.
Um, so we've been talking about some of the different issues with this drawing uh, and some of the problems we have with it. The first thing that was noted there, we said that there's no tolerances. The spacing and the sizing of the tooth here is underdefined. We have the width of the tooth, but we don't really have, maybe an ordinate dimension where you said the number of teeth and the location of each of them might be better. The location of the origin, kind of in the middle of the bottom part of this part, is not very helpful for us because it makes it difficult to determine what the total height of the part is, as well as verifying these dimensions is somewhat complicated, right? We don't have a dimension for this arc at the side here, this arc down here. And then I was trying to get some more feedback from you as to anything else you see in this drawing that is bad. So can you think of anything on here that's missing or poorly done? Who made this drawing? I mean, I made it, right? But nobody knows that. It doesn't have a name on it. What is this the drawing of?
Yeah, there's a drawing to see. There's no like little information at the bottom right corner.
There's no part number, there's no scale, there's no name. It's just dimensions, right? So, the annotation that tells the shop what that part is for, what lot it's supposed to be made with, what parts go adjacent to it, what the fits are and the clearances are relative to other parts. So there's a lot of additional information that should be included in the drawing that's just not there, right? So we have most of the basic geometry, but we're missing a lot of the additional information that's going to be important for that to work. And we actually don't even have all of the basic geometry. The reason we don't have all of the basic geometry is because I used relations when building out this part, right? But I didn't include any of those relations in describing the positions of the various parts, with the exception of the 20x.2 added on that because I wasn't going to remember how many there was of that. I guess I could have just guessed or counted or something, but so we'll make this part again in class. We'll talk about how to kind of use this, but before we do that, I want to talk about some basic aspects of dimensioning and tolerancing so that we're all on the same page as regards to some of the nomenclature here. I'd like to talk a little bit about the differences between linear dimensioning and geometric dimensioning and why we kind of care about that as a practice. I think that the key to creating good engineering drawings is to reflect on your drawings after you've made them. Most of the time, if you look at the drawing, you can identify, hey, it'd be better if I had this, or hey, this is missing. Better than looking at your own drawings is getting someone else to look at them, because it's a lot easier to see somebody else's mistakes than your own. So, before you send something down to the shop, have someone in your department take a look at it, have them see, especially if you have, a good-natured mentor or superior who's willing to take just a few minutes and say, oh yeah, you forgot to include this, that, and the other thing. It's going to save you a lot of back and forth, and you'll have a better impression with people outside your department, which is helpful a lot of times for those relationships. You kind of want to start with the part itself. If you're designing a part with an appropriate intent, then that's going to help to improve the part overall. It's going to reduce the cost and complexity of making it because you'll kind of have an idea of how that's going to be made. And you'll have included that when you are designing the various features. Obviously, if you can go to your assemblies and reduce the part count and reduce the complexity of the parts, that's going to make the drawings better as well because you won't have as many of them. And so the fewer you have to do, the easier it is to dedicate resources to making sure the ones that you have are done appropriately, right? You need to understand the material and manufacturing limitations. What do you need to include to make the part better in terms of the manufacturing capacity without changing the performance? So things like adding drafts or fillets for parts that are going to be molded, or not having pockets that are square on parts that are going to be milled, or trying to stick to polar geometries for turn parts or polar symmetry and things like that can help you to increase kind of the quality of those features. Yeah.
What's polar geometry?
Polar geometry,
Yeah.
like radial geometry,
Okay.
right? So trying to keep things, if I'm going to make a part that's going to be turned, do I have a way of making more of the features compatible with being made on a lathe as opposed to having to move to a mill and do additional processing, right? So the fewer kind of machine tools you can use in making the part, the better, right? You want to have the loosest allowable restrictions in terms of tolerances. There's a limit to that. I mean, once you get to a certain kind of size characteristic, then it doesn't really matter at that point. You can just have it be around that. If you're going something that's a tolerance larger than 1/100 of an inch, then just you don't need to do that unless you're talking really long lengths of material, right? So if I have a 10-foot span, then okay, yeah, sure, 1/100 of an inch might be appropriate. But if you have a part that's 2 inches wide and you want a 1/10 inch tolerance, any manufacturing process without any additional finishing operations is probably going to hit that. And even if it's just a band saw will hit that most of the time. If it's being used by someone who actually knows how to use it, right? And they measure before they cut, then they'll be appropriate. Well, like I said, they have to make sure to cut on the right side of the line at that point. But if you do, you'll be all right, right? So those are the kind of things you want to take into consideration. If you have parts that you can have multiple somewhat tight tolerances, that's often better than having to have one very tight tolerance. So you can look at doing tolerance stack up like we talked about last class and figure out where can you have looser or where do you need to have tighter features. And if you can distribute that, then that's usually better than trying to concentrate all your accuracy into a single part, right? I would worry more about clarity and consistency than I would about perfect adherence to industry standards. The standards are really there to give you the language you need to communicate your design. If you're not communicating it effectively in the first place, it's like you need to learn how to talk before you learn grammar, right? Like the rules of grammar do not help you if you don't understand the language and it at all, right? So learn the words and then learn about the grammar and the syntax. Basic terms, basic size, tolerance, and allowance. These are features that we're adding to the design of the part to help describe the allowable variation and size of the geometries. The basic size is basically the size of the part without regard to what that part is going to do or what the variance that is allowed is. The tolerance is the amount of variation that we're allowed to have, and the allowance is only in consideration between the interface between multiple parts. So if you have two parts that interface, the intentional gap or the minimal gap, I should say, or the maximal interference is the allowance. And so if you put both of the parts in the maximum material condition, which is going to change whether or not that's adding or subtracting geometry, but whether or not that's like a tab feature or a slot feature or a hole or a peg, it goes into that. There are different grades you can look at for that, and we'll look at those probably briefly as we go forward. The actual part is going to have its actual size, right? So what size is it when it's actually done being made? And then that size is going to have some amount of clearance or interference. There's going to be some gap or some overlap between the parts. There's never really such thing as a perfect fit, right? You got to keep in mind that SOLIDWORKS is always an idealized rendering of the part at the basic size, and your actual parts will never be the exact same as your SOLIDWORKS parts, right? There's always going to be some variation there. And even between multiple parts off the same production line, there's going to be some variation. If we look at a basic geometry, we have linear dimensioning, which is what we use kind of as the default for, our basic drawings before we really start looking at trying to ramp up and doing detailed design. If you're looking at, concept development, then probably this is going to be sufficient. It's really once you get to more advanced verification techniques that you start worrying about geometric tolerancing, right? We have to have a size and location for every feature. So in this case, the only thing that I'm dimensioning on here is the hole. We have the 3 and the 1.5 dimensions going across the bottom and the side. Those give me the location of the hole, as well as the tolerance for that location. And then the diameter of the hole is defined, as well as the tolerance for that diameter. The difficulty with linear dimensionings is that they're generally vague. And since you look at tolerance stacks where the position and the size variation will add together, we tend to have more kind of accumulation of error associated with that. So we take an example of kind of the variance in position. I've multiplied that 0.1 to a 40 times scale relative to the drawing on here. So you can see the variations a little bit more exaggerated. But if you take a center position on the extrema of those two linear dimensions, you can see the center can be anywhere inside this box, right? Because I've specified that position in kind of the horizontal and vertical direction can vary by plus or minus 1/100th of an inch. So anywhere in that box is where I can vary. And then I can also vary the width from kind of the minimum to the maximum material conditions, so the minimum maximum values, right, on the hole. And so this would be the allowable range inside that set for that position. And then you can kind of move that through all the different possible positions, and you get a total envelope of where the allowable size of or allowable faces of that hole are allowed to be. And so you get this kind of somewhat circular inner region, and then a somewhat circular, it's more like a square with rounded edges on the outer region. And the range of those face locations is oftentimes kind of much larger than what the original intent was because of the accumulation of those linear tolerance stack-ups, right? Also, this is only looking at kind of a location in one direction. We don't have any tools to control for kind of the straightness of the hole or the curvature of the hole or any other kind of more detailed features in the linear dimensioning scheme. Is that James? What's up, James?
Like other one, like not Minecraft launcher, like a.
All right, I can help you with that after class, okay? Sorry, my kids are off today, so they're in my office playing Minecraft. Apparently they want to be friends in the other Minecraft one, and they're probably trying to play on like the Windows as opposed to the Java version or something. Who knows?
We gotta stop class.
Yeah, you gotta sorry, you cancel class. Guys, gotta fix a Minecraft problem. No, I'll fix it later. So it's also, everything on here is also relational. So in a linear dimensioning scheme, we're always just giving the relationship between parts on the feature rather than relative to idealized planes. Whereas on a geometric scheme, we're really giving the dimensions relative to idealized planes. And so it makes the verification of those features via an automated process much easier than these kind of the things you would measure with a caliper, basically, right? So this is what a GD&T for the same part layout looks like. In this case, I have a datum A and a datum B. This is using the ASME Y14 standard, which is pretty much the default when it comes to GD&T. There's a equivalent or mostly equivalent ISO standard. I forget the number. And unless you're getting into the real nitty-gritty, there's not going to be instances where you're going to have a problem translating one of those into the other. If you only know ASME Y14 and someone gives you an ISO drawing, you'll still be able to read it, right? It's going to read out most of the same. You may have to look at some cross-reference chart or something like that at some point, but for the most part, it's going to be the same. So we have a datum A and a datum B here. Those datums are really defined by an idealized plane that is overlapping with the surface on that feature. If we want to, we can specify the tolerance on that surface relative to that idealized plane. I'm not going to get into all those, and we can also do kind of tolerances for each of those references. We have a lot of details inside there. But basically what we're saying here is that the center of this hole is 1.5 inches from the datum A. And then the center of the hole here is 3 inches from the datum B. The position of the hole, this is the position symbol, right, has a diametrical tolerance zone of 0.01 inches. And I guess I probably should have made that 0.02 since in this case, this is the diameter. And before I had it plus or minus 1. But you can get the idea. And that sets up a circular region where the center of hole is allowed to be in relative to the datums A and B, right? And then we also have the diameter, which is given as 1.5 plus or minus 0.01, just like we had in the previous one, but we've added the position tolerances to this box. Whenever you have numbers in boxes like this in the ASME Y14 standard, that just means that's a basic size. And so it's telling you the location without having to specify what the tolerances are. Yeah.
So the combined box on the top.
Yeah, the feature control frame.
Okay.
Feature control frame. Yeah.
So in the future, basically the tolerances from the two datums is stored in the feature control frame.
Yeah.
So that 0.01 is from B or A.
Well, so it is a position, right, measured relative to B and A, right? So B and A set up a coordinate frame that I can then use to measure that position. If I wanted to, if this was really a 3D drawing, I could have a primary, secondary, and tertiary direction to specify a position in 3-dimensional space, right? And the location of that position is given in the basic sizes, right? One of the things that can be confusing when you're looking at using the DIM expert in SolidWorks is that it knows where all the basic sizes are, but it's really asking you to do is specify what the tolerance values are. So I can actually go through and make a drawing or make a DIM expert set of annotations in SolidWorks that looks complete with a bunch of missing information. Because all of it's still in the actual part, it's just not being displayed on the annotations, right? And DIM expert is really looking to see, have you set up tolerances for all of the faces? And that's what it checks, right? So you can have basic sizes just totally missing and it doesn't care. At least doesn't tell you that you have those things missing. Yeah, well.
So that means that like if we want plus or minus 1.
So the 1.5 plus or minus 0.01, that is the diameter of the hole.
Oh, I know,
right?
like from because the 1.5 measure.
No, so it's, again, this is a position relation, right, with a diametric size. So you have this center position, right? That location is measured relative to A and B. And then the tolerance zone is actually round as opposed to being, plus or minus 1 in the direction. It's a circle with a diameter of 0.01, right? And again,
Centered at those distances from A.
yeah. And so again, this gives us the whole reason we use this GD&T is it gives us more ability to actually specify what the geometry of the allowable zones is, as opposed to the linear scheme where we have to use this kind of combination of multiple features to try and figure out what that means. So really it's about being more explicit about what you want the shape of the tolerance zones in 3 dimensions, right, to be. Does that make sense? And that's why we want to use our GD&T. We don't have time to cover GD&T in a lot of details, and I don't think it's really valuable to do that. It's one of those things where you're probably going to mostly learn by doing, because you just need to memorize what all the different language means, right? So it's like learning syntax, it's like learning a programming language. The only way you're ever going to remember and do it is if you do it a lot, right? One good thing that I did want to cover is this idea of rule 1, which is not a symbol, it's just a principle, is that the shape of parts is controlled by the original tolerance set unless otherwise specified. And what they're talking about here is that the dimensions themselves give you an envelope of what is allowable inside the part. In this case, they're just saying, hey, assume this envelope is this cylinder, right, in this lighter blue area with a diameter of 0.75 and a height of whatever that height is. Any allowable variation in shape is included inside that range. So it doesn't matter what the shape is, as long as it's inside the tolerance zone, then that is accounted as okay, unless you've specifically said, hey, it has to have this tolerance plus it has to have this shape, right? So in GD&T, one of the things that you're going to do once you get to kind of more advanced applications is you can specify things like, how cylindrical, how parallel, how, straight, how circular are the objects needing to be, in addition to those more general dimensions saying that, hey, the position of this is this value, right? So I could say that, I have a dimension that locates this and it has a position of, let's go back to our presentation. The hole is 3 inches from the left side. But if I care not so much about that position, but I care about how straight the hole is, I can specify, look, this hole needs to be within 0.01 degrees of perpendicular to whatever datum I don't have defined here, like the page, right? So say datum C, right? And that's what I care about. I know the size, the location position, that can have a huge variance, right? So if what you care about is straightness or flatness or whatever, there's a symbol in GD&T that will allow you to specify, yes, this is exactly what I want from this part, rather than having to adopt tight tolerances kind of more globally to achieve that feature, right? Which is going to be more expensive, right? The cost of tolerancing is difficult to assess because, again, it's just a function of what manufacturing equipment you have. Most of the time, the additional cost is because you have to go from one set of operations to a new set of operations. This is a chart from, I guess, a reasonably old text at this point, talking about some measurements that they did of costs of different finishes. And they used basically a finishing turn on a lathe, which is doing the same or just doing another operation on the same machine, right? So if I can finish this with just a roughing turn, it's like, say you take a cast part and I take it off of the, take it out of the mold, right? And I throw it onto the lathe and I only need to do a rough pass to get the tolerance that I want, then it's going to be reasonably cheaper, right? To get that finishing pass, I have to do the roughing pass first to cut it to close to size. And then I do a secondary pass to get it even closer, and then a third pass to get even closer to hit these tighter tolerance ranges, right? So that's what kind of these ranges are down here. The reason this goes to 0 is that once you get to a tolerance zone that's large enough, then you're starting to say like, okay, look, it came off the casting. I don't need to do any additional processing, and so it doesn't cost me anything. So it's not that if you have a very large tolerance zone, your cost of the part is going to be 0. It's just you're probably not going to need any additional operations past whatever bulk processing you had to begin with to get to that operation, to that size, right? So if it's all being done on the mill, you're basically doing roughing for the entire thing and then you're done. Once you get past that operation on the mill, this jumps up significantly if you need to start grinding or honing that to get these very, very tight tolerances kind of in this sub 1,000th of an inch range. So this is a half of a thou. And this is a quarter of a thou down here. And you hear that language quite a lot in manufacturing, just because that thousandth of an inch is a nice round number. And so most of the things are made kind of that level of accuracy if you're looking at machining them manually or even on a CNC. The CNCs are not really that much more accurate than a person running the mill, at least than a trained person running the mill. They're just automated, right? So the advantage there is that you don't have to pay the person to run the whole time. You have to pay someone to set it up, but once they set it up, doing a second run. It's like we were talking about before with the program and then print, right? So you get everything going once. That original setup takes a lot of time. But then once you've got it done, you throw a piece of material in, you clamp it down, you hit print, you walk away, you come back a few hours later, you take it off, you put on the next one. If you've got 5 machines, you load one, you hit print, you go to the next one, you load it up, you hit print, you go to the next one, you load it up, you hit print. By the time you've got all of them loaded up, you're back on the first one, unloading that part, moving into the next operation and proceeding with that, right? So as the technology advances, the ability to hit like slightly taller tolerances on kind of a like a CNC machine or something like that does get a little bit better, but it's not like orders of magnitude better. So if you want like an order of magnitude increase in accuracy, you're going to require some additional special case processing, which is going to probably, you know, significantly increase the cost of production of that part. Yeah.
You said that a thousandth of an inch is like a common.
It's a kind of a common, like we can hit this inside milling and turning, like basic machining operations without specialized equipment, right? So if you throw something into a mill, you can probably expect to get a thousandth of an inch tolerance without having to work too hard, right? You know, you can get a hundredth of an inch tolerance without trying, right? Like if you go to the mill and you say, hey, cut this to this size, even using like a huge bit, right, and not trying very hard, it's going to get to that hundredth of an inch, right? To get to that thousandth of an inch, you're probably going to want to do, you know, at least one roughing pass and then a finish pass to get a, you know, a smoother, flatter surface that's right at that size. And there's a lot of things that contribute to that variance. You know, it's the stiffness of the machine, it's the wear of the tool, it's all the different things that can affect it, right? How well fixtured it is. Again, putting parts into the right place in the milling machine is probably like 90% of the work, right? Especially if you're running on a CNC, because you got to worry about how do I locate this and hold it in place while it's being kind of manufactured without it coming loose, right? Or bending or anything else, right? Or the machine hitting the thing that I mounted it to, as opposed to the part I want to work on and then breaking something, right? Or just ruining my mounting piece. Or the machine, this is possible. Standard tolerances, if you are super lazy and you don't include tolerances on your dimensions, they will assume or should assume that the tolerance is based off the decimal precision included in the drawing. So like in my bad example here, did I close it? I guess I closed. This is in millimeters. I didn't say it's in millimeters, but it's in millimeters. So if I have 0.00 millimeters, then I'm going to assume that my tolerance is plus or minus 0.01 millimeters. If I go back to my cost chart here, that puts me in this grinding range, right? So that assumption of all the features being plus or minus 0.01 millimeters, that's a pretty tight tolerance to apply globally to my drawing, right? And especially for features like the teeth on there, I probably don't care that all those teeth are exactly 0.20 millimeters wide, right? They probably just need to be somewhere between like 0.1 and 0.2, honestly, right? Like, because they're there to provide grip to a tissue. They're not there to, you know, position other parts, right? Now on like the holes for pins that are going to go into here, I didn't really describe what this part is for, but this part is basically part of a grabber. So it rotates about this top hole and then gets pulled by a bar attached to this bottom hole. And then it kind of rotates on that to grab onto tissues, right? As part of a arthroscopic tool. And so this size diameter here, because there's going to be a pin going through there, it's going to be a reasonably tight fit because it's, you know, these are intricate pieces. This one probably does need to be something close to that 0.50. But again, I'm going to use a bit that's specifically sized to get that sizing, so that won't be too hard. Everything else on here could probably, you know, plus or minus, you know, 1/10 of a millimeter, maybe not quite that much on some of the features where you have relatively thin geometries on the side. Just worrying about this getting too thin. If this dimension here is 0.4 and this one were to be this minimal condition at 0.9, then some of those walls might get a little thin. But I could oversize that a little bit more to kind of compensate for that as well if I wanted to. So kind of give you guys an idea of kind of how small is too small how big is too big in terms of tolerancing. And this is going to change based off your manufacturing process as well. So, if you don't care, make it bigger and people will be able to hit it, right? You want to have the largest tolerance zone that will still work for your part. These are different classifications for fits. So you see we have clearance fits here, transitions fits, and interference fits. They're basically graded as to what the range of values would be for a shaft and a hole. So this is the hole size, this is the shaft size, and you have a basic dimension for that hole, and then kind of what the sizing should be. This is in micrometers, right? So in millimeters, and this is the basic size in millimeters. What those tolerance zones and clearance or allowance or negative allowance interferences should be, right? So you can look those kinds of things up. This is actually an ISO standard. And so if you wanted to pull that out, you got to pay for it, but you can use those to specify what type of sizing you want. Right. Again, this is kind of looking at more like the grammar stuff. I wouldn't worry about that until you need it. So another thing I want to talk about is just kind of knowing where the failure in your tolerances on your parts is most likely to be. A lot of the times when you're manufacturing something, your ability to manufacture it is going to be limited by specific aspects of the design. So assume you have a block, right? And you're going to locate that block into another part, and you want it to rest flush on the left and bottom sides inside that groove, right? So if you imagine this being a thicker part here, and then there's this pocket gray part which is cut out into that, then I'm going to use that pocket to locate that block. Does that make sense? That's what I want these parts to do. And what I care about is the position of this, I guess, purple block relative to this gray block. That's the key characteristic I want to try and preserve. So I can come down here and I can specify, okay, here I want to have a plus or minus 100th of an inch tolerance on each of those surfaces. And that's going to give me position of the block. And I'm going to cut this on a mill. Well, milling an interior edge like that is really difficult because I'm using round bits. I'm going to be dragging across this surface, right? And pulling that out. So without having to do a specialized operation, my option to fix that is to use a really, really small bit to try and get that corner cut out, right? And I can do that, but probably what you're going to end up is something that looks like this. This is my tolerance zone. This is the maximum material condition in red and the minimum material condition in green. And this is my corner, right? And you can see that I can stay inside that range, but I have to get a really small bit to cut that out, and it's still rounded. And there's going to be a gap, if you imagine this block kind of resting on this maximum material condition edge between those faces. And so it's not going to locate it very well. So what are some things I could do to fix that without looking at the next slides?
That sounds hard too.
Round the block, it's an additional operation. That's not bad. What else?
Fillets, such as rounding it.
Yeah, fillets, rounding it out. Anything else? But so I can round the block. I can also include that round on my gray piece as well, right? And there's a couple other things I could do. And I guess,
Design geometry.
was that?
Change some of the design geometry to make like the slot could fit in, like a little protrusion from the purple block, and pull, like the slot.
Yeah, something else that locates that feature besides just the walls, right? Yeah, I mean, so basically we have a couple different options. We can change the block that it's fitting into by adding a corner. So now that's easier for us to manufacture, right? And then I can do the same kind of modification to the block to get rid of that, right? I could also just I could put a chamfer on the block or anything that would relieve that corner, right? I can also remove some additional material out of my support piece, right? Such that I can still have a larger radius, but I don't have that corner, right? And this kind of operation on a milling machine is actually pretty easy to do. I just program the mill to go to that corner and then go into the corner a little bit, come back out of the corner and then go up, right? Now I've got that cut. And if I don't care that there's a little bit of a gap around this corner, just the positioning is what I care about, then that works out great, right? Again, the advantage of this is it didn't require that I had to modify the block to get that to fit in place anymore. And now I don't really care at all about the tolerance on this hole, right? All I care about is the tolerance on this edge right here and the tolerance on this edge. So I can cut that kind of all the way down, do a little loop, and then come back out, and I'm good, right?
So you have a tolerance like that hole where you don't care. You don't want to
Just give it a big value. Yeah, yeah. So, you can give it a plus or minus 1/100 of an inch or something like that, right? Yeah. And that's the advantage of having, not using just a default tolerance scheme for the entire thing, right? If your tolerance is the same everywhere, then going through all the effort of doing stuff like this is not worth it, right? Like you might as well just have something that looks like that and just let them make it to whatever it's going to be. It's like, yeah, I don't care. They're just whatever, right? And if you're prototyping or something, maybe you don't care, right? Like, I don't know what any of these fits should be yet. Just make it as cheap and as fast as you can. I'm just going to print it on the printer. If you're printing it on a 3D printer, the tolerances don't matter, right? It's going to be what it is when it comes off the printer based off what you sent it. The slicer does not change the accuracy of the slicing based off the tolerance you specified. Not that advanced, right? And again, you can adjust for that by changing the basic size of the part in the CAD model, but it's still going to be what it is when it comes out, right? But if you take this and you give it to a machinist or you give it to someone who's doing like a mold design or whatever, then yeah, they're going to interpret your drawing and then they're going to change the mold based off what you want it to be, right? And they may remake your part in CAD too. They may say like, well, I have this, I need to remake it so I get the geometry to send to my CNC machine. And they may use the same software you use, and they may not. They may make it in a different software. They may make it in the same software, but remake it anyways because your model tree is so bad that they can't extract features from it anymore, right? I think, yeah, all right. So let's practice. Let's go ahead and make this part. Let's try and make it a little bit better than we did. We got 10 minutes. So we'll probably have enough time to make the part. And then what I'll have you guys do is make a drawing of the part yourself sometime between now and next week. And then you can submit that for your assignment for this week. All right. But let's make the part together so we can be consistent about what the geometry is intended to be.
Our game starts at 9:30.
Yeah, we got 10 minutes, right?
10 minutes.
So we're gonna be out here at 9:27.
We're cutting it close.
All right, 5 minutes.
I don't want to use the rest class.
We'll take 5 minutes. Then 9:20. Well, it's 9:20 now. You guys just want to make the drawing? Yeah. Okay. I'll tell you what. I'll take 10 minutes to make the part so it's on the recording. And then if you guys want to, you can go back and you can watch the recording to make the part. So I'll make it fast. Does that make sense? All right. I do want to talk a little bit about the design intent on this. On this part, I do want to kind of assume that I'm going to be milling this part out from round stock, right? So really what I'm starting with is a bar that has a diameter of 4 millimeters. I'm going to set my units to millimeter gram second. I'm going to go to the right plane just because I want that to kind of be that right side right here as it's shown in there. And I'm going to make a circle that has a diameter of 4 millimeters. Then I'm actually going to make that a guiding curve by changing it to a construction geometry. You do that just by clicking on the part. I didn't click it first. I got to click it and then click on make construction. And then I'm just going to use that as a guide to do an arc across the top. Now in my drawing here, you notice that the origin is still in the middle. That's probably a good spot for the origin from the CAD standpoint and making that make sense for drawing out these different pieces. But I don't want to use the dimensions that I'm given here. I want to make those a little bit more explicit, as well as a little bit more intuitive relative to the faces that I'm going to be milling out. So what I might want to have is actually have a reference point on the top of this block. So that way I can define these positions relative to that same out exterior datum, right? That idealized plane on the top of my part. So I'm going to put my sizes here relative to that. And this is going to be 1. And I'm going to have everything that I can kind of go back to that same feature. That'll be 3. This width is still going to be 2. All right. Good luck on your exam. And this width is going to be 1. And one of the things that I can do is that even if I have dimensions that I want that are not given, like this relationship, I want this to be centered. I'm trying to get this to stay on here. Come on, you. Let's zoom in. I can have driven relations or driven dimensions that specify the size of these parts later on. So I'll make these equal. And again, we're fully defined there. If I make these two collinear, now I can extrude this out to a total height of 5. And the reason I want it to look like this is because I can cut that from my round stock pretty straightforward. I'm going to cut out the side view and my teeth. So I'm going to go to my front plane. Let's sketch on that. I'm going to use a corner rectangle to specify how far that would be. And then that could just be one pass on the mill. And we'll specify that as being, actually, let's do everything relative to the base of this. Try to keep this foot media controls hidden. So I'm just going to leave that one. I'm going to mention these relative to the right side. That's 1. That one's already defined, so we don't need to do that. All right. We'll do our holes. And again, if I want to use the same reference point for my other drawings for the holes, I really want to define them relative to that top surface. Now, in this one, you might argue it'd be better to have them relative to the bottom as they are shown in this drawing. Because you're going to have to reorient this to cut this operation anyways. But I don't know if that is, I don't actually know if that's going to be better from a manufacturing standpoint or not. I do want these to be 0.5. I do want them to both be the same. So I'll make those equal. In these texts, I can add to indicate that those are 2 holes of the same size. Although you probably want to do that inside dim expert or in your annotations rather than in the part itself. Cut those out. Get that geometry there. Now the curvature bits, which is one of the issues that we had in regards to making those cuts, are actually cut out to allow this part to rotate about this center hole without interfering with the other parts in the assembly. So I'm going to use arcs to cut those out, and I'm actually going to use relations to define them. But what I want to do, oh, wrong spot, is later on I can add annotations to those parts to make sure that they are fully defined in my drawings. Again, if I have a single line bisecting the entire part, I can use that to do a cut to make that curvature. Do the same thing on the bottom side. And they're rotating about this one. Oh, keep missing that first click. There we go. Again, if I want to, I can specify those dimensions inside my sketches. I just gotta make them driven. But really, you probably want to do that just inside your annotation. If you want to include them inside your inside your parts, you can, but probably not necessary. Do one actually. Looking good. Just gotta add my teeth. The reason this one had kind of underdefined was that it was an equilateral triangle. Again, the idea that I'm using relations to define these positions, which it fully defines the part, but at the same time, I want to make sure. What is that doing there? Here. I want to get the midpoint of this and make it coincident with that edge there. There you go. But again, I can add additional relations to this as driven dimensions if I wanted to include them inside the sketch. Or again, you can remember to include them as part of your annotations after the fact. I'm going to use the spacing of 0.2. I'm going to do 20 of these. Should be good to go. All right, so please take some time and make a drawing for this part. Try to make it as complete as possible and submit that prior to our class next week.
Thank you.